Before we discuss the theory behind, or further discuss the theory behind integration, let me do one more example, which is still going to be given for a function f of x equal to x squared. And we're going to try to figure out the area under the graph of x squared on the interval from 0 to 1 by using the ideas that I already described in a previous lecture. So what I want to do is to compute two things. So let's call this another example. So let's suppose, or actually, let's consider a partition of the interval from 0, 1 by intervals, or by n intervals of equal length. So we're going to use this partition to approximate the area under the graph of f of x equal to x squared on the interval from 0 to 1. And if you recall the definition of a definite integral from calculus, right integral was the difference between the area above x-axis and the area below x-axis and your graph. That means that we want to compute or to approximate first integral from 0 to 1 of x squared dx, right? Because you already are familiar with definite integration, then really this is not such a difficult thing, right? You know that the answer is going to be x cubed over 3, right? You take antiderivative of x squared on the interval from 0 to 1. The answer is going to be 1/3. But I want to arrive at this answer at this point without using any antiderivatives because we're developing a theory, so we're assuming that we don't really know anything about how to integrate. Okay, so let's see how we should proceed. So we discussed in the previous lecture that I can use, somehow I can try to work with overestimation of the area and overestimations and underestimations. In particular, because f of x equal to x squared is an increasing function, then if on each subinterval we're going to take as heights of rectangles values of the function at the right endpoint, then we're going to always get an overestimation. In fact, the largest possible overestimation by using a particular partition. And if I use a right endpoint, then on each interval, then that means that I'm using the smallest feasible approximation of the area on a given rectangle. So for the same partition, uh, we're going to consider different heights of rectangles on different intervals. And remember that I used the notation S and O for overestimations and S and U for underestimations. So red, in this case, is going to be the largest possible overestimation on each interval. Now, why is it the largest? If, for example, we're looking at this rectangle in this particular interval, then clearly it makes no sense to approximate uh, the area under the graph by a rectangle which, for instance, is going to have this height, right? Because it's beyond the range of the function on this interval. So the largest value of the function on a given subinterval is going to give us the largest possible overestimation by using rectangles. So we're going to consider separately red approximation and green approximation. So if I'm looking at, all right, so first of all, let's make a small change here. Let's call this partition P. So what do we have? What do we know about P? So P is going to consist, partition is just partition points. If I label my initial point x0 and I label my final point xn, that means that I have n intervals between 0 and 1, and I have n plus 1 points, right? Because if I start counting points from x0 and I end up with xn, right, then the overall number of points is n plus 1. So P has n plus 1 points, x0, x1, etc., xk, etc., and then the last point is going to be xn. And we can find actually the formula for what xn is. So again, let's look at the picture. We subdivided the interval from 0 to 1 into n pieces, right, of equal length. So that means that each piece is going to have length delta x, which is 1 over n portion of the length of the entire interval. Entire interval has length 1, and so that means that delta x, the distance between two neighboring points in a partition, should be 1 minus 0 divided by n, so over n. And then, so to get to x1 from x0, I'll just need to move by 1 delta x. To get to x2, I'll need to move by 2 delta x. x3, I need to move by 3 delta x from the initial point. So if I want to get to xk, I'll have to move by k times delta x. So that means that xk in this partition is equal to k times delta x, and again delta x is equal to 1 over n, right? 1 over the length of the interval. And xk, of course, ranges from 1 to, or in fact, we can even make it range from 0 to n. Okay? So if k ranges from 0 to n, then we have our n plus 1 points. All right. So that gives me my partition. And so then the largest overestimation of the area, or again, of the integral from 0 to 1 of fx squared dx, using the partition P. Is going to be S, the Riemann sum using n subintervals, overestimation. That is what? That is a sum of areas of red rectangles. And the red rectangle has a height equal to the value of the function at the right-hand point, right? So the first rectangle has a length, has a height equal to the value of the function at x1. Second red rectangle has a height equal to the value of the function at x2, and so on. So that means that Sn0 will have the area height of x squared at the point x1. So it would be x1 quantity squared. And the width of all intervals is exactly the same and equal to delta x. Second rectangle will have an area x2 squared. We'll have the area x2 squared times delta x plus so on until you reach a last rectangle. And the last rectangle, again, will have a height at its right endpoints. The height at the right endpoint of the last interval is xn. So it's xn squared times delta x. All right. And I can express this by using sigma notation. So this is a sum n from 1 to infinity of what? Xk squared times delta x. Okay, so that's the largest overestimation. Then remember, if I use green rectangles, that will give me the lowest possible underestimation. And the only difference between red rectangles and green rectangles is that the height of a green rectangle is going to be the value of the function at the left endpoint of each subinterval. So the lowest underestimation P, using P again, is going to be now S underestimation using n rectangles of equal length. So we're using left endpoint, so this will be x0 squared times delta x. The left endpoint of a second interval is x1, so it's x1 squared times delta x, plus etc. And then let's look at the last rectangle. Last green rectangle has a height given by the value of the function at xn minus 1. So plus xn minus 1 squared times delta x. And again, by using the sigma notation, then this is a sum and starts from 0, goes, and by the way, my formula before was bogus, because the index is k, so k starts at 1 and ends at n. So here, k will start from 0 and end at n minus 1. And then I have again xk squared times delta x. So sums look pretty similar, but they're not exactly the same, right? So in the first case, I'm starting at 0 and I end at 10. And in the second case, so in the first case, I start from 1 and I end at 10. And in the second case, I start at 0 and I end at n minus 1. Okay, so fine. So then we can rewrite these expressions by using the fact that we already know that we can express xk in terms of delta x and k. And so then, just going back to the first formula, as overestimation, largest overestimation by using n rectangles of the equal length is going to be a sum k from 1 to n. What's xk? Xk is k times delta x. So k times delta x quantity squared times another delta x. I can simplify this a little bit. So this is the same thing as a sum k from 1 to n. If I open the parentheses, this is k squared times delta x squared. There's another delta x. So k squared times delta x quantity cube. Now delta x is a constant that is independent of x. So delta x cube I can factor out. And I have a sum k from 1 to n of k. And then you might recall that at some point, again, in the past, we figured out what the sum from 1 to n of k is. And I'm going to recover this formula in a second, but before that, let's look at what we can say about SU. And so it's a similar sum. In fact, it's exactly the same sum, except that it starts from 0 and it ends n minus 1. So still k delta x squared times delta x. Open the parenthesis and factor out delta x cubed, and you get delta x quantity cube times the sum k from 0 to n minus 1 of k. Okay, fine. So we have that. So now let's recall that formula that I had just mentioned. Recall that. So let's call AK, or rather let's make it AM. That is equal to the sum n from m from not m L from 1 to m of L. What is that? That is 1 plus 2 plus etc. plus m, right? But I also can write AM in the following way. So if I can write AM like that, I can always reorder the way in which I'm writing AM, and I can write it as m plus m minus 1 plus etc. plus 2 plus 1. I'm going to put m minus 1 here as well. Plus m minus 1, that's the next to the last guy, and the last guy is m itself. So then if we add these two formulas, these two equations, what we get is 2 times AM is equal to, I'm adding the first two terms, I'm going to get 1 plus m. Then I'm adding next two terms. I get 2 plus m minus 1. 2 plus m minus 1, that is again 1 plus m. Then it will be 3 plus m minus 2, that is again 1 plus m. And you continue like this. Next to the last term is m minus 1 plus 2, that's again 1 plus m. And finally, the last term is m plus 1, so it's again same thing as 1 plus m. How many of these 1 plus m's would I have? Right, I'm adding terms from 1 to m, so that means that there should be m of these terms. So altogether, this will happen m times. And if I add m plus 1 to itself m times, then what is that? That's 1 plus m, or m plus 1, that's the same thing, times m. And so then we conclude that am must be equal to m plus 1 times m over 2. Right, so the sum of all integers from the first one to the mth is going to be that last integer that you're adding times m plus 1 divided by 2. And so now if I use this formula in my expressions for overestimation, for largest overestimation and smallest and lowest underestimation, so here I'm adding all terms, all k's from 1 to n, which is the same formula as here, except I'm using different letters. But using dummy letters really makes no difference, right? Those dummy letters will disappear. So that means that as n o should be delta x cubed, and then the sum of actually, sorry, again, what I'm saying here is bogus. This was k squared and not k. Sorry for that. So rather than doing this, let me give you another formula, because the formula that I need is in fact not the sum of k's, but the sum of k squares. I'm not going to prove that formula, but I'm just going to show it to you. In a similar way, we can show that the sum m goes from, or L goes from 1 to m of L squared, that is going to be equal to m times m plus 1 times 2m plus 1, and the whole thing is going to be divided by 6. Right. So you can prove this formula in a similar way, but we're not going to touch it here. So let me just modify this a little bit. Am was what? It was a sum L from 1 to m of L's. All right, fine. So let's go back to overestimations and underestimations. So once again, as overestimation by using n intervals is going to be delta x cubed times the sum k from 1 to n of k squared, and I can use the second formula that I'm writing here, with m being equal to n and L being k, right? Again, this is just a notation. The expressions should work in a similar way. So this is delta x raised to the third power, and the sum of k squares from 1 to n will be n times n plus 1 times 2n plus 1 divided by 6. One way, in fact, to show that this formula is valid is, of course, by using induction, right? You can show that it is valid for m equal to 1, and then you can prove by using induction that if it is valid for m equal to, let's say, k, then it should be valid for m equal to k plus 1. Okay, so, all right. Then I remember what delta x was, right? Delta x was a length of a subinterval in a division of the interval from 0 to 1 into n equal subintervals. So we immediately got that delta x is equal to 1 over n. So then this guy should be equal to 1 over n cubed, right? Times n plus 1 times 2n plus 1 over 6. And I can simplify this a little bit by getting rid of n. So this should be n plus 1 times 2n plus 1 divided by 6 times n squared. Okay? So this is my overestimation. What about underestimation? It should work in a similar way. So underestimation by using n intervals of equal length. That was delta x cubed. So that was the smallest possible underestimation. Times the sum k from 0 to n minus 1, right? That was the only distinction that you're adding things between different limits, still of k squared. And then, of course, if I'm adding k squared starting from 0, when k is equal to 0, I get no contribution from that term. So I can start as well from k equal to 1, and I still have to end at n minus 1, and this is sum of k squareds. So this should be delta x cubed, and then I have to use this formula with m equal to n minus 1. So what's that? That's n minus 1, then n minus 1 plus 1, and then finally 2 times n minus 1 plus 1 divided by 6. And then just like in the case of the overestimation, delta x is 1 over n cubed, so 1 over n cubed. And then I have n minus 1. Then n minus 1 plus 1 is n. And 2 times n minus 1 is 2n minus 2 plus 1, so 2n minus 1 whole thing over 6. Now, once again, I can get rid of n, and I'll get n minus 1 times 2n minus 1 over 6 n squared. Okay, so now let's see what else were we able to show before, right, when we discussed possibilities of using these overestimations and underestimations. Overestimation is always larger than the area under the graph of a function. So it's always larger than the integral. So this should be greater than the integral from 0 to 1 of x squared dx. And underestimation, of course, must be smaller. So this number is less than the integral from 0 to 1 of x squared dx, right? Okay, so then we said that if I take all possible underestimations of the area under the graph of my function, using any possible type of intervals, if the intervals are of equal length, not equal length. Let me scroll back to where we were. Right, so when I consider any possible partition of my interval, like what is drawn in here, then this is an underestimation. In fact, it's a lowest possible underestimation by using a specific partition, right? Because again, the value of the function at the left-hand point is the smallest possible value of a function on a given subinterval. So this thing always is an underestimation. It doesn't matter what interval I'm considering. And we said that we hope that the area under the graph of the function is going to be somehow the largest of these possible underestimations, or supremum overall possible underestimations. And in a similar way, when we consider all possible overestimations for all possible partitions, then for all of them, the approximation is going to be larger than the actual area under the graph of a function, or integral from 0 to 1. And so therefore, if I take infimum over all possible partitions, the largest approximation using any partition that I can imagine, then the infimum should probably be close to the actual area. And so now I'm going to test that idea. And one other thing is that we do expect that any overestimation is larger than the area under the graph, and any underestimation is smaller than the area under the graph. And so therefore, that was one of the conclusions that we drew in here, that any overestimation I expect to be larger than any underestimation by using any two partitions, P and Q, whatever partitions I can think of. So let's try now to use what we found if we employ the ideas that we just mentioned. Okay, so then if I take the infimum over all possible partitions of my interval from 0 to 1 of infimum over all overestimations using any number of intervals, n, p, whatever. So in fact, I'm going to use a different letter here. Let's say st. I have t intervals, so it may have equal length, it may have unequal length. What can I say about that infimum? I can say that for sure it must be smaller than this one overestimation that I was able to compute explicitly, right? So if I'm taking the infimum over all possible partitions, then it must be smaller than the value of the area approximation by using my specific partition with n points and intervals of equal length. So this infimum then must be less or equal than my S and O, which is, once again, n plus 1 times 2n plus 1 divided by 6n squared. And in a similar way, if I'm taking the supremum over all possible p's of overestimations, SUT, this should be greater or equal than, right? Supremum is greater or equal than supremum of the set is greater or equal than any element of the set. So this should be larger than the particular area approximation for my specific partition. So it should be larger than SNU, which was, once again, n minus 1 times 2n minus 1 over 6n squared. Okay? Okay, so, but if that is the case, then, of course, I compute it as ON for a specific n, right? But, of course, this should be true for any n, right? So this is true for any n in n, and so this is true also for any n in n. And then what can I say? I can say that if I let n go to infinity here, right, if this number is less or equal than this number for any n, if I take n to infinity, then this number is going to be still less or equal than the limit of these quantities when n goes to infinity. So therefore, infimum over all p's st0, right? This number is independent of n. That's an infimum over all possible partitions. So this should be less or equal than the limit n goes to infinity of n plus 1 times 2n plus 1 over 6n squared. And likewise, the supremum over all p's of STU should be greater or equal, so it's greater, this number is greater or equal than this number for any n, so therefore the same inequality should survive in the limit as n goes to infinity of n minus 1 times 2n minus 1 divided by 6n squared. And what can I say about these limits? Well, so as n goes to infinity, both top and the bottom goes to infinity, but both top and the bottom are polynomials. And so then you know that the limit of the ratio of two polynomials should be the same as the limit of the ratio of the highest powers that you see. So in this case, the highest power on the top is going to be 2n squared. Highest power on the bottom is 6n squared. So the limit is the same as the limit of 2n squared over 6n squared, which is 2/6 or 1/3. And a very similar thing happens here, though, even though this expression is not the same as an expression above, it's smaller, right, because it's an underestimation. As n goes to infinity, top goes to infinity, bottom goes to infinity, highest power of n on the top is n squared, it has a coefficient 2. On the bottom, it's 6n squared, 2n squared, or 6n squared, 1/3. And so this limit is equal to 1/3. And so what can I conclude from this? What is the meaning of this term? SOT is any overestimation of my integral by using t intervals, right? So if I take infimum of all overestimations, then I'm kind of saying that the smallest possible overestimation of the area under the graph, or of the integral from 0 to 1 of x squared dx, that this is equal to 1/3. And likewise, the largest possible underestimation of the same thing, of the integral from 0 to 1 of x squared dx, that is also equal to 1/3. But what does this tell you? So I'm taking overestimations of the integral from 0 to 1 of x squared dx. I'm considering all possible overestimations like that. I take the infimum, and I see that the smallest overestimation is 1/3. Then the second thing is that, so the second statement is that the largest possible underestimation is also 1/3, but actual area should lie between these two numbers. So therefore, that means that the integral from 0 to 1 of x squared dx is actually equal to 1/3. This is a true statement, right? That we know that this is true. Let me see if I want to say anything else here. So I hope that this makes sense, right? So by considering largest overestimations, largest underestimations, and smallest overestimations, then taking advantage of the fact the actual area must lie between these two numbers, we find that the area, or the integral, must be what the area must be, right? Because largest underestimation and lowest overestimation will give me the same value. Now, it might turn out that if I do a different example, it might turn out that the smallest possible overestimation would be strictly bigger than the largest possible underestimation. Well, what would that indicate? It would mean that I cannot really probably speak about the area under the graph of my function, at least by using these approximations with rectangles, because if smallest underestimation, overestimation, and largest underestimations are not the same, then that means that there is something wrong with the graph of my function. And so I would like you to keep this picture in mind, or this discussion, this example in mind, when we're going to just delve into the theory next. I'm going to use different terminology, and the terminology is going to be sort of maybe heavy at times, but keep in mind that whatever I will be saying is going to be precisely what I'm saying here. I'm always going to consider overestimations and underestimations, and then I'll make a largest underestimation, then I'll compute the largest underestimation and smallest overestimation, and as long as they're the same, then that would mean that my function is integrable and the area under the graph makes sense.